First few problems we'll solve primarily using phasors. Without deploying writing equations, etc., we'll do it purely using phasors. All right. A quick and gentle reminder of what we've been doing as far as phasors are concerned. If there is a particle oscillating between these two limits, P and Q, with O being the mean position, the convention that we have adopted, I mean, any convention is fine, but staying put with that convention is important. So, if a particle oscillates between these two limits, so while the oscillator is at Q, its auxiliary particle coincides with the position of the oscillator. While the oscillator moves to the left, the auxiliary particle covers this part. While the oscillator comes here, the auxiliary particle is here. While the oscillator goes down, its auxiliary particle traverses the lower half of the circle, right? And there is, for every position of the oscillator, a unique position on the auxiliary circle. The position of the auxiliary particle could be marked, right? This is the whole idea. And the angular frequency of the oscillator is synonymous with the angular velocity of the particle executing uniform circular motion, the auxiliary particle, that is, right? One more thing. Now, if at t equal to 0, we have the oscillator at Q. If at t equal to 0, we have the oscillator at Q, then the description of this oscillation is going to be x equal to a cos omega t, right? If at t equal to 0, we have an oscillator at O and moving rightward, then the description of this oscillator is going to be x equal to a sine omega t. If the oscillator is moving leftwards at t equal to 0, then the description of this oscillation is x equal to minus a sine omega t. If at t equal to 0, the oscillator is at this extreme, then the description of this oscillator is going to be x equal to minus a cos omega t, and so on. Right? Now, with these ideas, so the ideas are as simple as this, right? Using these ideas, we'll try and communicate with the problems of the sheet. So this is the amplitude position, and we have a particle oscillating between these two limits of the diameter, and at time t equal to 0, the particle P is at x equal to a by root 2 and is heading towards the mean position, right? That means now its corresponding point on the auxiliary circle would be P prime and would be heading like this. Yes or no? Now think of an oscillator Q. At the same instant of time, this oscillator is here. Now the description of the oscillation of this is going to be given by x equal to a cos omega t, right? Now the oscillator P has its auxiliary particle here, where the oscillator Q has its auxiliary particle here. So which means the oscillator P is ahead in phase by an angle theta compared to Q. Compared to Q, the oscillator P is ahead in phase by an angle theta. Look at the angles that the corresponding particles on the auxiliary circle describe at the center. That's the phase difference. And therefore, P is ahead in phase compared to Q by an angle theta. Yes or no? And theta, as you can easily witness, is pi by 4, because this a by root 2 by a is cos theta. Yes or no? Cos theta is 1 by root 2, leading to theta equal to pi by 4. Right? And therefore, if the description of Q is x is a cos omega t, then the description of motion of P is going to be x equal to a cos omega t plus pi by 4. Why? Because identical to Q, but ahead in phase by an angle pi by 4. The other way of looking at it is the following. This is P, and its auxiliary particle is here, P prime at t equal to 0. This is x equal to a by root 2. Now you can think of a benchmark particle which is at O. So this is P. Let's say there is a particle at Q which at time t equal to 0 is heading to the right. Its auxiliary particle would be at Q prime. Its auxiliary particle would be at Q prime and would be moving in this direction, right? Now, what's the motion of Q? The motion of Q at time t equal to 0, x is 0 and is moving rightwards. So Q is described by x equal to a sine omega t. And the auxiliary particle of Q is Q prime. Now, the motion of P then, realize the auxiliary particle for P is P prime here and is ahead in phase by this angle compared to Q. P is ahead in phase compared to Q by this angle. But what's this angle? Pi by 2 plus pi by 4, 3 pi by 4. So if the motion of Q is x is a sine omega t, the motion of P is going to be given by x equal to a sine omega t plus 3 pi by 4. Yes or no? Are you fine with this? And you know, the two would actually be the same because cos theta is the same as sine 90 plus theta, right? So this could have been written as a sine omega t plus pi by 2 plus pi by 4, which is a sine omega t plus 3 pi by 4, etc., which matches with that. So, you know, in any given situation, you might want to choose your reference particle as a cos omega t, a sine omega t, etc. Compared to that, find the phase difference and write your equation for the particle under the spanner commensurate. Got me? So either way, it's fine. Is that all right? Problem 2. Find the distance traveled by a particle executing SHM of time period t, amplitude A, in a time t equal to t by 12, starting from rest. That means it must be at its extreme position, at the amplitude position at time t equal to 0. So the particle that we are seeking is here at time t equal to 0, right? And obviously the only way to go is leftwards. Now, in this time t equal to t by 12, the corresponding point, so P comes to P prime, P comes to, let's say, P1, and its auxiliary particle goes to P1 prime. Yes or no? That means the angle that the auxiliary particle describes at the center is theta. In a time t, the auxiliary particle describes an angle theta, which is omega t. So which is like omega is 2 pi by t into t, which is t by 12, which is pi by 6. Pi by 6 is the angle described. So theta is pi by 6. And the distance travelled by the oscillator is pp1. And pp1 very clearly is, this length is a minus a cos theta. A minus a cos theta is the distance covered by the oscillator in this time. So a minus a cos theta, which is a minus a cos 30 degrees. So which is a into 2 minus root 3 by 2. That's the distance travelled by the oscillator in a time equal to t by 12. Yes or no? Right? Problem 3. Two particles executing SHM about x equal to 0. One particle P given by a sine omega t plus phi 1. The other particle q given by a cos omega t plus phi 1 could be written as a sin omega t plus pi by 2 plus phi 2. I would rather convert both to sine or both to cosine, right? So that's why I add this pi by 2 so that it could mean the same, right? Same amplitude, same omega. Now, at time t equal to 0, the particle P is at x equal to a by root 2. At time t equal to 0, the particle P is at x equal to a by root 2. And moving to the right from the mean position, moving to the right from the mean position. While the particle at Q is at x equal to minus root 3 by 2 into a, moving towards the left from the mean position, right? Now, if P is moving to the right, its auxiliary particle would be right here, P prime, and would be moving like this. Clear? If Q is moving leftward, its auxiliary particle would be Q prime and would be heading in this direction. Clear? Evidently, realize that this angle is pi by 4. Yes or no? Because this length is a by root 2 and OP is a. So cos of this angle is a by root 2 by a. So this angle is pi by 4. This angle, pi by 6 is 30 degrees, pi by 6. Right? And therefore, this angle is 5 pi by 6. This angle is 5 pi by 6. And the phase difference between P and Q is going to be pi by 4 plus pi by 6. This is going to be the phase difference between P and Q, yes or no? Right? That means phase of Q minus phase of P is going to be this angle pi by 4 plus pi by 6, yes or no? Right? So then, phase of this, which is pi by 2 plus pi 2, phase of Q minus phase of P, which is pi 1, that's equal to pi by 4 plus 5 pi by 6. Yes or no? And therefore, phi 2 minus phi 1 would be readily available. Phi 2 minus phi 1 would be readily available to you. Got me? 505. 7 pi by 12. 7 pi by 12. So it turns out to be 7 pi by 12. Phi 2 minus phi 1 is 7 pi by 12. Two bodies execute SHM with the same amplitude A and time period T. This is the line of oscillation. Amplitude A and time period T. When one of the blocks is located at the right extreme, say P is located at the right extreme, the other is located at the equilibrium position. So Q is located at the equilibrium position and is heading leftwards. Q is located at the equilibrium position and is heading leftwards. Find the smallest time in which both the blocks will have the same displacement from the equilibrium position. That means they would be at the same point. They would be at the same point from the in respect of the equilibrium position, right? Okay. Realize that P is obviously also heading leftwards because that's the only way it could go, and Q is heading left. So then, while Q reaches this extreme, P comes from the extreme position to the mean position, right? And then P moves in this direction, whereas P retraces. So you would expect P and Q to meet somewhere here. You would expect P and Q to meet somewhere here, right? So P obviously has, in the process, P has come all the way, has crossed O and has arrived here. P has come to, let's say, this point, call it P1. Q has gone this way and has reverted, and this is Q1. For P then, since P is still heading in the leftward direction, the auxiliary particle for P is going to be P1 prime right here. Is going to be P1 prime right here. Right? For Q, realize what the auxiliary particle has done is, the auxiliary particle was originally located here, and it covered a quarter of a circle, and then it went down because Q was then heading leftwards, rightwards, and then Q came to this Q1 prime. Q came to this Q1 prime. And P and Q bumped into each other, and that's what happened. Right? Now, evidently, the two auxiliary particles would have described the same angle at the center, no matter what. Because they travel for the same time, the two auxiliary particles would have described the same angle at the center of the auxiliary circle. Clear? This is the triangle of relevance. Evidently, this angle is alpha, this angle is alpha. What's the angle described by the auxiliary particle P at the center? Pi minus alpha. Right? P describes the auxiliary particle for P goes from P to P1 and would have described this at the center. But this angle is pi minus alpha. So P describes an angle pi minus auxiliary particle of P describes pi minus alpha at the center. Pi minus alpha at the center. Now, Q, realize that the auxiliary particle for Q starts from here, it goes down here, pi by 2, and then plus alpha. Pi by 2 plus alpha is the angle described by the auxiliary of Q at the center at the same time. And they must be the same. This must be pi by 2 plus alpha. Right? This is the angle theta that both describe at the center of the auxiliary circle. Yes or no? Hey, theta is what I want to find. If A is equal to B, then each will be equal to half of A plus B. Yes or no? So if theta is what I want to find, alpha is not my interest. Right? If A equals B, then each will be equal to half of A plus B, so that alpha gets eliminated in one shot. Right? Each is equal to 3 pi by 2. So 3 pi by 4. And the time taken to describe this angle, is going to be, well, to describe 2 pi, t seconds. So to describe 3 pi by 4, these many seconds. Yes or no? Time per unit radian into radians will give you the time. Yes or no? So this would be the time, which is 3t by, in 3t by 8 seconds, this is the shortest time in which they would bump into each other. Got me? Right? Can I wrap this off? Are you all certain about everything that I am saying? Two bodies execute SHM with amplitude A and time period T. When one is at the right extreme, the other is at A by 2 moving leftwards. Find the shortest time in which both the blocks will be at the same point on scale. Find the shortest time in which both the blocks will be at the same point on scale. Hey, again, originally the auxiliary particle for Q would be Q prime here, right? And cos of this angle would be half, A by 2 by A, half, so this angle would be pi by 3. 60 degrees is what this angle would be. Now, Q, P is heading leftwards and its auxiliary particle is coincident with it, right? And is heading in this direction while P is heading here. The auxiliary particle is describing the circle like this. Q travels this way and reaches the right extreme and then retraces. During its retrace, it bumps into P somewhere here. Call it P1, Q1 is where they bump into each other. So that this is while Q is retracing and P is still traveling leftwards. So if P is still traveling leftwards, its auxiliary particle would have been right here, P1 prime. And since Q is traveling rightwards, its auxiliary particle would have been, let's say, Q1 prime here, and would be moving like this. This would be moving like this. Yes or no? Right? And in the same time, both the auxiliary particles would have described the same angle at the center. Now, if this angle is alpha, this angle will also be alpha. What's the angle described by P at the center? Pi minus alpha. The angle described by P at the center when they bump into each other is this angle, pi minus alpha. What's the angle described by Q at the center? 2 pi by 3 plus alpha, yes or no? See, this angle is 2 pi by 3 plus alpha is the angle described by Q at the center, the auxiliary particle of Q at the center, and they are equal. And then each must be half their sum. So 5 pi by 6, each will be equal to 5 pi by 6. So the angle described at the center is 5 pi by 6. So the time taken to describe 5 pi by 6 is going to be 5 pi by 6 divided by omega, which is 2 pi by t, which is 5t by 12. These many seconds is the shortest time in which they would bump into each other. Clear? Not a problem. Now, it's the motion fundamentally would still be simple harmonic, but truncated and a curtailed simple harmonic motion. In the sense that this particle would go to the leftmost extreme A unit, the amplitude position. This is its mean position, and would have liked, had the wall not been there, it would have liked to go all the way A units to the right. But then it encounters this wall, undergoes an elastic collision, perfectly elastic collision, and its journey to the right gets prematurely curtailed. And it's the velocity with which it hits is the velocity with which it rebounds, because it's a perfectly elastic collision, right? And then it goes this way, it goes to the leftmost extreme, and then reciprocates between x equal to minus a to x equal to plus a by 2, right? Now, had the wall not been there, the omega of the motion would have been root k by m. The time period would have been 2 pi by omega. Yes or no? Now, the manner in which we want to define the time period of this revised situation is, well, if this particle mass m starts here, it has to go all the way to the wall, and it has to come back to this point. That would be my revised time period. That would be my revised time period for the oscillator. See, when it goes from this end to the wall, it goes as per the dictation of this time period, right? It doesn't understand the wall until it hits the wall, right? And then it hits the wall. The only difference that it makes is it's not able to go further. But when it reverts, it again goes as per this time period. So the auxiliary particle, see, so then on the auxiliary particle front, this is what is happening. This is the mean position now, right? This is the leftmost extremity which it can maintain. But then on the rightmost front, it doesn't go all the way to this end, right? This is x equal to a by 2. X equal to a by 2. Which means now this particle, this part of this particle mass m, while it's here, its auxiliary particle is here at this extreme, right? And then it starts moving to the right. The auxiliary particle begins to traverse the lower half, right? When the mass m comes here, the auxiliary particle arrives here. Yes or no? Right? Which means now the angle described at the center by the auxiliary particle is this. In order to hit the wall, this is the angle that it describes at the center of the circle. Yes or no? Theta. This is the angle that it describes at the center of the circle. Clear? Now, this angle is pi by 3. A by 2 divided by a. So, this angle theta is 2 pi by 3. Therefore, the time taken by the auxiliary particle to traverse this, which is the same as the time taken by the oscillator to hit the wall, to go all the way to the wall, it takes time t equal to theta divided by omega. So, 2 pi by 3 divided by 2 pi by t. Yes or no? Which is t by 3 is the time it takes to hit the wall. Yes or no? Now, once it hits the wall, it's the auxiliary particle suddenly jumps here. Right? Now, for this particle to go back to this extreme, the angle that the auxiliary particle once again describes is 2 pi by 3, and the time taken would be t seconds once again. So, t seconds to go here and t seconds to come back. T seconds. So, the time period would be the 2 times small t, that is 2t by 3 would be the time period for this revised oscillation. 2t by 3 would be the revised time period for this oscillator, right? So then, as far as the auxiliary particle is concerned, this is the prohibited part of the circle. So, you still have an oscillation, but a truncated oscillation of this kind. So, that is the only difference. In the earlier case, it would have traversed this point, but this region, but now this is a prohibited region for the auxiliary particle. This is the prohibited region for the oscillator. Clear? There is no loss of energy because it's a perfectly elastic collision. Had the wall not been there, it would have gone to the right extreme and it would have come back to this point, but with a velocity in the opposite direction. That's all. There is no loss of energy. It's a perfectly elastic collision. Like I said, there is no loss of kinetic energy at all. Right? And this is, the wall is massive. So V is E times U. E is 1. So V is U. But the direction changes. Right? Same thing, same thing, same thing. Not an issue. I mean, all that he's saying is that, well, we could have done this T by 4 and then another 30 degrees, which would be T by 12. 30 degrees covered at T by 12. So T by 4 plus T by 12 into 2. This is fine. I hope all of you are there with me on everything that I have said so far and you're perfectly clear about things, right? There is an oscillation with time period equal to 4 seconds, starting from A by 2, moving in the positive direction. We have this oscillator, which at a certain instant of time was at A by 2 and was moving in the positive x direction, obviously this direction. And we want to find not the displacement, but the distance traveled in 15 seconds. Distance traveled by the oscillator in 15 seconds. So in t equal to 15 seconds, we want to find the distance. Oh, all right. Now, in a full time period, the distance traveled would be 4a. Yes or no? Right? In a full time period, the distance traveled would be 4a. Now, here you have 3 full time periods plus 3 seconds. Right? Here you have 3 full time periods plus 3 seconds is what you have. Right? So now, in 3 full time periods, it would have traveled 12a, because in a full time period, it travels 4a. So in 3 full time periods, it would have traveled 12a, right? Plus. Now in 3 full time periods, it would come back to this position, yes or no? It would come back to this position heading in the same direction, and by then it would have traveled 12a units along the line of oscillation, right? Now 3 seconds left. Now in 3 seconds, by the way, at this instant then, that is at t equal to 3 times capital T, the auxiliary particle is here and is moving in this direction, yes or no? The auxiliary particle for P is at P prime at t equal to 3t seconds and is moving this way Clear? Now in 3 seconds, what's the angle described by this? In 3 seconds, realize that 2 pi is described in 4 seconds. So in 3 seconds, this is the angle described, yes or no? Right? So this is the angle which is 3 pi by 2. 270 degrees would be described by the oscillator in 3 seconds. In the remaining 3 seconds. So then, locate the auxiliary particle like this. This is 60 degrees. This is 60 degrees. So then, the auxiliary particle goes here, describes 60 degrees. the oscillator comes to this point while the auxiliary particle reaches this point, right? And then it describes another 180 degrees. So that makes it 240 degrees. That means now the auxiliary particle has done all of this. The auxiliary particle has done all of this. The auxiliary particle did this and then did this entire upper half of the circle. But then it still has to describe 30 degrees more at the center, 180, 240 and 30 more degrees at the center. So 30 more degrees at the center, the auxiliary particle comes at P double prime with this as pi by 6, 30 more degrees at the center, right? Which means now the auxiliary particle has done this, and has done this. What about the oscillator? The oscillator has done this, and has done this. This is what the oscillator has done, right? So then, by the time it's at P, it has already done 12A, right? And then it does this. This is another A by 2, right? And then it does this, which is 2A. And then it does this residual amount S naught. And this residual amount S naught, by the way, this is A. This length is A root 3 by 2, A cos 30 degrees. And therefore, this length is A minus A root 3 by 2. Yes or no? This is A units. This is A root 3 by 2. So, S naught is going to be A minus A root 3 by 2. That's the residual S naught, right? So, A minus A root 3 by, that's the total distance S covered in 15 seconds. Got it? Can I write this off? Two particles executing SHM with the same omega and the same amplitude, or rather amplitudes A and 2A, same omega but with amplitudes A and 2A, on the same straight line with the same mean position, cross each other in opposite directions at x equal to A by 3 from the mean position. Find their phase. Okay. Realize that they had the same mean position, so same center for the auxiliary circle. But the auxiliary circle of one is A units, the auxiliary circle of the other one is concentric and of radius 2A units. This is A, this is 2A. Now, they cross each other in opposite directions at x equal to A by 3 from the mean position. At this point, one of them is moving to the right. Let's say the one with amplitude A is moving to the right. Its corresponding point on the auxiliary circle would be P prime. So this is the auxiliary circle of relevance for the particle of amplitude A, right? If it's heading to the right, its auxiliary particle would be P prime here, right? This is O. For the other particle, it's heading in this direction and its auxiliary circle is this, amplitude 2A, and therefore its corresponding point on the auxiliary circle, is this q prime. So no, right? And this point is x equal to a by 3. This point is x equal to a by 3. Now, if this angle is theta 1 and this angle is theta 2, then the phase difference is going to be theta 1 plus theta 2. The phase difference is going to be theta 1 plus theta 2, yes or no? Right? The angular separation between the corresponding auxiliary particles, is theta 1 plus theta 2. That's going to be the phase difference, yes or no? Right? So, the phase difference delta phi is going to be theta 1 plus theta 2. Evidently, sine theta 1, as you can see, sine theta 1 is a by 3 divided by a, so 1/3. Sine theta 2 is a by 3 divided by 2a. A by 3 divided by 2a, that is 1 by 6. That is 1 by 6. So theta 1 is sine inverse 1/3, theta 2 is sine inverse 1/6. So theta 1 sine inverse 1/3 plus sine inverse 1/6. Bolo? Oh, sorry. I'm so sorry, cos theta. I'm so sorry. Yes, I apologize for this. This is cos theta 1, cos theta 2. I'm so sorry about this. Cos theta 1, a divided by a by 3, and cos theta 2, a by 3 divided by 2a. I'm so sorry. So cos inverse 1/3 and cos inverse 1/6. Theta 1 and theta 2 are cos inverse 1/3 and cos inverse 1/6. Clear? Shall we proceed? Both are cos inverse here. So pi by 2, you'll have a pi then. Pi minus sine inverse 1/3 minus sine inverse 1/6 is what you'll get. Okay. See, theta 1 plus theta 2 we got as cos inverse 1/3 plus cos inverse 1/6. Right? But cos inverse theta is pi by 2 minus sine inverse theta. So this will be pi by 2 minus sine inverse this. This will be pi by 2 minus sine inverse this. So that makes it pi minus sine inverse 1/3 minus sine inverse 1/6, if you like to convert it into sine. What's the big fun in doing this? Until and unless you have options in a problem given in terms of specifically sine inverse, cos inverse, then you do this. Otherwise, this is as good or as bad as this. Okay. So problem 9. A particle of mass m free to move in the xy plane. I hope all of you are there with me on everything that I am saying, right? Because you can't leave these concepts to chance. You have to ensure that you're absolutely at home with all these ideas. They're easy, but for sure you have to understand them. Huh? And you should be ready to apply them as and when required. I mean, you don't always write huge equations and you solve those equations. Wherever possible, use the auxiliary circle treatment for simple harmonic motion, right? This is what you want to do. A particle of mass m free to move in the xy plane, subject to a force F, which is minus kx I cap minus ky j cap, where k greater than 0. The particle at time t equal to 0 is released at 2, 3. The particle is released at a point 2, 3 at time t equal to 0. Essentially, what we'll do is, there are two forces acting on the particle. One in the x direction, minus kx, one in the y direction, which is minus ky, right? So, kx of magnitude kx units in the x direction and of magnitude ky in the... Clear? This is what is happening. Now, what we'll do is, we'll superimpose the effect of both these. We just imagine, let's say, kx to be present for a moment. The particle is at x equal to 2. The particle is at x equal to 2 and is experiencing a leftward force towards this direction. It therefore would execute simple harmonic motion x equal to 2 cos omega t, because at t equal to 0, x is 2 and the force constant is k. So, the omega would be root k by m. So, this particle, because of this, would have its x coordinate at any given instant of time. This is x equal to 2 at time t equal to 0. I have already mentioned that. T equal to 0. So, x equal to 2 cos omega t would be the nature of motion because of a force acting in the x direction, restoring in character. Yes or no? Because when x becomes negative, f becomes positive. So, in all cases, it's directed towards this direction. So, it's restoring. So, motion would be simple harmonic, and at t equal to 0, x is 2. So, that's the maximum x possible because it's at rest. So, this must be the amplitude position in the x direction. So, then everything matches when you select x is 2 cos omega t as the description of motion in the x direction if nothing happened in the y direction, right? But now, things are simultaneously happening in the y direction because there is ky acting, downwards. So, then the description of motion in the y direction, 3 cos omega t would be the description of motion in the y direction, yes or no? Right. Therefore, check this, x by 2 minus y by 3 is 0. This would be the locus of motion. This would be the locus of the oscillator. It's going to execute simple harmonic motion, not along the x-axis, along the y-axis, but along a line x by 2 minus y by 3 equal to 0. So, 3x minus 2y equal to 0 would be the line of simple harmonic motion executed by this. This is the locus of the oscillator. 3x minus 2y equal to 0 is the required locus. Got me? Fair enough? A particle performs SHM as given by x is a cos omega t. Determine the distance travelled by the particle in t seconds, not the displacement, because the displacement is given by this in t seconds. The distance in general. Find the generalized expression for the distance covered by the particle in t seconds. Clear? Essentially, the particle is here at time t equal to 0. The particle is at x equal to a. The particle is at x equal to a, time t equal to 0 and is heading leftwards. Now, one thing, in a quarter of a time period, you know, the auxiliary particle covers a quarter of a circle and the distance travelled is amplitude A. In every t by 4 seconds, starting from here, in t by 4 seconds, the distance travelled by the particle, the oscillator, is going to be the amplitude. Right? So now the first question is, how many t by 4s are there in t seconds? So there would be a certain number of t by 4s and there would be a residual, right? So when you divide t by 4, when you divide small t by t by 4, it will leave a remainder and it will have a quotient, right? So t could have been written as n into t by 4 plus a remainder t naught, where t naught would be less than t by 4, because when you're dividing by t by 4, the remainder t naught has to be less than t by 4. Yes or no? So n is the quotient of the division of small t by 4 and t naught is the remainder of the division. Given any t, you can divide by the time period. Time period is known because omega is known. You can divide that time, 100 seconds are given. You can divide that by a quarter of a time period, you will get n. The quotient will be n. And whatever is the remainder of that division, that will be t naught. Yes or no? If t naught is less than 1/4 of a time period, and therefore the distance travelled in t naught seconds will be less than the amplitude, right? So essentially then, the distance travelled is going to be n times the amplitude plus the distance travelled in t naught seconds plus the distance travelled in t naught seconds, which will be less than the amplitude. Yes or no? Are you fine with this? Do you understand what I'm saying? Okay. The particle starts from here. The particle starts from here, heading leftwards. I mean, if t naught was 0, then there is no issue at all. Then it's going to be n times a, right? But if t naught is not 0, that means it's not full quarter time period, then you will have a residual t naught out of this division, right? And the quotient could have been even or odd. And the quotient of this division could have been even or odd. N times the time, quarter of a time period. No? Say n is even. Say n is even. Even means an even number of quarter periods. An even number of quarter periods. See. O is this. This is the other extreme. This is 1 quarter period. This is 2 quarter periods. This is 3 quarter periods. This is 4 quarter periods. 5, 6, 7, 8. Which means every time there are even number of quarter periods, the particle would be at one of the extremes. Even every time n is even, then an integral multiple of quarter periods would cause the particle to be here or for definiteness. Let's say at time t equal to n times t by 4, the particle is here. The particle is here. And in that time, it would have covered NA meters along the line of oscillation. Now the auxiliary particle is going this way, well, the oscillator is going this way. What's the remaining time? T naught seconds. This is taken care of. Nt by 4, Na meters. Right now in T naught seconds, the auxiliary particle would have come to this point, P prime. The auxiliary particle in T naught seconds would have covered this arc of the circle. It would have been less than the amplitude because T naught is less than T by 4. So in T naught seconds, the auxiliary particle would have covered this as the arc and would have described an angle theta naught at the center. Where? What's theta naught? Theta naught would have been omega T naught. Theta naught would have been omega T naught, right? Therefore, this distance, this is A. So this distance would be A cos theta naught. This distance would have been A cos theta naught. But the distance travelled by the oscillator, while the auxiliary particle reaches here, the oscillator travels this S naught. The oscillator travels this S naught. So what is the S naught? S naught is A minus A cos theta naught, right? So the required distance S up to Nt by 4 is going to be Na for n to be even plus S naught. S naught very clearly is this, which is A minus A cos theta naught. A minus A cos theta naught is S naught in the residual T naught seconds. So far so good, right? Now the last writes on this. A minus A cos theta naught. Theta naught is omega T naught, right? Omega T naught. But T naught is T minus NT by 4. T naught is T minus NT by 4. So far so good, right? Which is Na plus A minus A cos omega T. But omega into time period is 2 pi. Omega into time period is 2 pi. So this into this is 2 pi. So this will be n pi by 2. This will be omega into t is n pi by 2. So minus n pi by 2 for n to be, when n is even, this is the distance traveled by the oscillator in t seconds. Whenever n is even, the distance traveled by the oscillator starting from the rightmost extreme is going to be Na plus A minus A cos omega t minus n pi by 2. Yes or no? Now let's look at the case where n is odd. N is odd. Are you confused? Udit? No? Let's see what happens when n is odd, right? N is odd means, it starts from here. 1 time, 2, 3, 4, 5, 6. That means it has to be at the mean position. It could either be heading rightwards or it could be heading leftwards. Does not matter. So then let's say at time t equal to nt by 4, when n is odd, it's at the mean position. And say it's heading rightwards. It's heading. And the corresponding point on the auxiliary circle would be P prime and would be moving along this quarter of the circle. Now, in the remaining T naught seconds, the auxiliary particle would have gone from P prime to P double prime and would have described an angle theta naught at the center, where theta naught would have been omega times T naught, T naught, yes or no? And the oscillator. So while the auxiliary particle does this arc of the circle, the oscillator goes from the mean position to this position. The oscillator goes from O to P, yes or no? So O to P would be referred to as S naught. The residual distance in the residual time T naught would be S naught. And if this is theta naught, realize that this will be theta naught. Alright, this is A. So S naught is A sin theta naught. A sin theta naught is S naught. Yes or no? So S naught in this case is A sin theta naught, where theta naught is omega T naught. Theta naught is omega T naught. Omega T naught, where T naught I can write as T minus NT by 4, which is A sin omega T minus N pi by 2. That's S naught. So the total distance is going to be Na plus S naught when N is, and when T naught is 0, obviously Na would be the total distance traveled. Got me? Any better method? As far as I can imagine, this is the best you could do with it. But for sure, if you come up with something better than this, share it with me, right? I don't think you can do more than this, right? Now let me tell you that there is an approach which is an energy approach in oscillations. In the sense, so far we've dealt with what's called the force approach. We've caused an elongation by a certain amount, we've identified forces, and we've determined that force proportional, net force proportional to displacement from the mean position and restoring in character, and concluded that the motion is simple harmonic and so on. This is what we've done, right? The other approach is the energy approach. Spring of force constant K. This is the natural state of the spring. Mass M. Bless you. Imagine an intermediate state of motion of the mass M, where it's displaced by an amount xi. So the spring would have got elongated or compressed depending on the direction by an amount x, and in that state the velocity of the masses Now the energy of the oscillating system, the total energy of the oscillating system in this intermediate state is half mv square plus half kx square. If there are no dissipative forces, which is what you expect in a typical oscillating system, right? No energy losses. So E would be the same for all x. That means E should not depend on x. E should not depend on x. It will be the same for all permissible values of x. That means dE dx must be 0. If E does not depend on x, then the rate of change of E with respect to x ought to be 0. E does not depend on x, if E is independent of x, if E is independent of x, dE dx must be 0. There is no rate of change of E with respect to x. That's what it means, right? Now, so if I differentiate E with respect to x, then I get V squared when differentiated would give me 2V dV dx, 2V dV dx plus kx. That must be 0, which means V dV dx is minus k by m into x. But V dV dx is what? Acceleration. V dV dx is the acceleration A. So A is minus k by m into x, and therefore helping us conclude that the motion must be simple harmonic with omega squared equal to k by m, omega equal to root k by m, etc. A is minus k by m into x would guarantee simple harmonic motion, right? So now this is the energy approach, and very strongly pursued in situations where there is greater amount of sophistication, intricacy. Although to a simple situation of this kind, we could still apply the same end and we could arrive at our result here, right? Now, suppose you have a pulley like this, fixed pulley, and there is a spring that passes around the pulley. And an overhanging mass M. A spring of force constant K. Let's say this designates this whole thing is the spring. This designates the natural state of the spring, that is unstretched state of the spring. This level is the natural length of the spring, which is bound round it. And I can call it the zero of potential energy. Zero of potential energy of the mass M. Zero of potential energy of the mass M. The mass M has gravitational potential energy. When the mass is above this, I'll say, if it's, let's say, 5 units above this, it will have potential energy mg into 5. It's 5 units below this, its potential energy would be minus mg into 5. If I choose this as my zero of gravitational potential energy. Right? Now, think of an intermediate state of this mass. Think of an intermediate state of this mass, x units below this natural state. By the time the mass has descended x units, let's say it's acquired a velocity v. The spring also would have got elongated by an amount x, right? What's the total energy of the system then in this intermediate state? Well, half mv square plus half kx square minus mgx, right? So again, d dx will still be 0. d dx will still be 0. So we have like a mv dv dx plus kx minus mg, which must be 0, right? Or we have v dv dx, which is the acceleration, as minus k by m into x plus g, right? The motion therefore is simple harmonic. The only difference is x equal to 0 is not the equilibrium position. The equilibrium position would be x equal to mg by k. Equilibrium position would be governed by a equal to 0 or f equal to 0, right? So the motion is simple harmonic, but its mean position is not the state or the natural unelongated state of the spring. It's x equal to mg by k is the equilibrium state for the oscillator. The omega of oscillation will be root k by m for sure. The omega of oscillation will be root k by m for sure, right? Now, let me modify this. Make changes. Let me work around variations of this pulley. Can I wipe this off? Whenever you want to oblige me, do this. Now I have a spring of force constant K. This is a spring, but this is a string. This is a string. That's a spring. Right? Now, this pulley would obviously descend because the spring will experience a force, right? Essentially, so this was the original position of the pulley. Its center was here. This end of the pulley, this point of the pulley is connected to this end of the spring. Now, when the spring elongates by a certain amount, when the spring elongates by a certain amount, the pulley moves down by the same amount. The pulley will move down by the same amount. So in an event where the spring has elongated by an amount x, pulley has also descended by an amount x. All right. Now, this was the original thread, right? So then when the pulley comes to this position, do you realize that x units on either side of the pulley will get released? There would be x units of thread on this side of the pulley and x units of thread on this side of the pulley, which should be free now, free length of the thread. This would be free length, right? Imagine two things to happen, one after the other, pulley descending and action on this segment of the string pending, right? This goes down, so there would be a certain free length of the string and a certain free length of the string. This wrap up length would come around this, and this length x and this length x, which is 2x units, would result in descent of the mass m. So when the pulley moves down by an amount x, the mass m would have descended by an amount 2x, yes or no? When the pulley moves down by an amount x, the mass m descends by an amount 2x. Are you fine with this? Right? Now, once you understand this idea, that means the pulley moves down by an amount, or the spring elongates by an amount, half the descent of the mass, clear? Now, in this, again, let's say this is the point where the spring is in its natural state. All right, and this is x equal to 0. After a while, say the mass m descends by an amount x. The pulley now will extend by an amount x by 2. The spring will extend by an amount x by 2. This will extend by an amount x by 2. So, in a state of this kind, let's say the mass m has developed a velocity v. Let me write down the expression for total energy, and this also I look upon as the zero of gravitational potential energy, right? So the total energy E is half mv square, kinetic energy of the mass, and then half k x by 2 whole squared, elastic potential energy of the spring, because the spring has got elongated by an amount x by 2. So half k into x by 2 whole squared, elastic potential energy of the spring, and then minus mgx as the gravitational potential energy of the mass, minus mgx. Yes or no? Right? So dE dx is mv dv dx plus k by 4 into x minus mg. This must be 0, right? Leading us to v dv dx equals minus k by 4m to x plus m plus g. Obviously, v dv dx is not 0 at x equal to 0. The equilibrium position would be 4mg by k. From this state, the equilibrium position would be 4mg by k. And the omega would be root k by 4m. This would be simple harmonic motion with omega equal to root k by 4m. Time period would be 2 pi by omega. Time period is going to be 2 pi by omega. Got me? Let me combine this and the previous now. Let me create a concoction of the two. This case and the one that I discussed prior to this. Spring of force constant K1 another spring of force constant K2. Overhanging mass. Now, think of a state where this spring has got elongated by an amount x1. This spring has got elongated by an amount x1, right? Now, an elongation of this spring by an amount x1, if this was a string, would have caused the mass to descend by an amount 2x1, right? So this, because of this alone, would have descended by an amount 2x1, right? Now, imagine in the same time, this spring to have elongated by an amount. Now, the elongation of this spring would completely reflect in the descent of this mass m. So, this mass m would have, and therefore the descent of this mass would have been x equal to 2x1 plus x2. Now, by the time this mass has descended by this amount x, it's developed a velocity v say. It's developed a velocity. Now, let's see if x1 and x2 are related. Let's see if x1 and x2 are related. Look at the free body diagram of the pulley. This spring has got elongated by an amount x1. So, the spring will exert a force k1 x1 on this pulley. Spring will exert a force k1 x1 on this pulley, yes or no? And the force in this entire spring, this lower spring would have been k2 x2. So, then at the tangential positions, they would have been like we've done before, k2 x2 and k2 x2. If this is of negligible mass, then k1 x1 must be 2 k2 x2. k1 x1 must be 2 k2 x2. And x is 2x1 plus x2. So, using this equation and this equation, can I not solve for x1 and x2? In terms of x, I can solve for x1 and x2. So, both x1 and x2 would be known in terms of the displacement of the mass m, which is of relevance, right? So, then if I have to write the energy equation, E is going to be half mv square for this, half k1 x1 square for this, half k2 x2 squared for this, minus mgx. All that you need to do here is replace x1 and x2 in terms of x from equations 1 and 2. Differentiate with respect to x, put d dx equal to 0 and then write v dv dx equal to something. So, v dv dx would be minus of something into x, that something would be the omega square. Finish. That's all that. You know what I'm saying? Say now. This is the only spring. The mass m is horizontal. and these two, oh, in fact, all are movable pulleys because this is connected to a spring, so this will also move. And I want to find the omega of oscillation for the system for the mass n. Now, one thing, in any given state, whatever be the extension of the spring, total length of the string will not change. The total length of the string, this is the string, that's not going to change. Say Ls, the position of the spring, will change with time. Ls, this is the end of the spring, it's going to vary with time, right? Let's say this portion of the thread is L. This portion of the thread is L. Now, what's the total thread length? L plus L, 2L plus this length is L minus Ls plus L minus Ls. 2 into L minus Ls plus the wrap-up lengths are anyways constant. The lengths wrapped around the pulleys, they don't change at all. So this is a constant, right? So which means now this is a constant, so half of this is also a constant. So which means half of this is L plus L, 2L minus Ls. So 2L minus Ls is a constant. That means 2 times change in L would be change in Ls. Why? Because if I take change of this, that must be the change of a constant, but change in a constant is 0. Change in a constant is 0. And change of this, change of 2 times L would be 2 times change of L minus change of the spring length. That's 0. Yes or no? So change in spring length would be 2 times the change in this L. Change in this L. Yes or no? Right? Okay. Let's say this is the state where the spring is natural. Now, when the mass descends by an amount x, then the mass descends by an amount x, this L would increase by an amount x because this pulley would also descend by an amount x. So L increases by an amount x. So if change in L is x, then change in the spring length will be 2x. Change in the spring length would be 2 times change in L, so 2x. Yes or no? So when this descends by an amount x, the spring elongates by an amount 2x. Spring elongates by an amount 2x, yes or no? And when the mass reaches this position, let's say, V is the velocity of this mass. V is the velocity of this mass, clear? So let me go ahead and write the energy expression in this state. Energy expression in this state. The energy expression is going to be half mv squared, kinetic energy of this, and then half k, 2x whole squared, half k, 2x whole squared, minus mgx. E has to be independent of x, so dE dx must be 0, d dx must be 0, v dv dx 4kx minus mg, this must be 0, mv dv dx 1, v dv dx, and realize that if you v dv dx then turns out to be minus 4k by m into x plus g. So the equilibrium position can be obtained by plugging in this equal to 0. The omega square for the oscillation is 4k by m. So the omega is going to be root 4k by m is going to be the omega for this oscillator. time period is. Got me? Not a problem so far, right? Now, with these ideas in place, you should be able to deploy energy methods to a variety of situations, right? Of course, to any situation it could be deployed, but there are times when it's evident, the force is very evident, and you don't have to work through complications. You apply the force method. So you apply your discretion when to use energy methods and when to use force methods. It's your discretion. Now that I have conveyed to you these ideas on energy principles, what you might want to do is very quickly attempt problem numbers 11 and 12 right away. 11 and 12 should not take you. Find the period of oscillations of the system shown. Hello, people on that bay. So this is the natural state of the spring. Like I said, as long as we can successfully write our energy expressions, it's taken care of. Now, when this mass m moves to the right by a certain amount, x, the pulley with which it is integral will also move to the right by the same amount. So which means when this pulley moves to the right by a certain amount x, and this pulley moves to the right by a certain amount x, it leaves 2x units of thread free. It leaves 2x units of thread free, which goes around this and results in the descent of m. So m descends by an amount 2x. This is the zero of gravitational potential energy when x was 0. And by the time this reaches, descends by an amount 2x, let's say this mass m acquires a velocity v. Mass m acquires a velocity v. When it moves to the right by an amount x, this acquires a velocity v, but the velocity of this would be 2v, because this is moving twice as much as this mass m. So the velocity of this would be 2v, right? So now the energy expression, half mv squared for this mass, half m 2v whole squared for this mass, the spring gets elongated by an amount x, so half kx squared for the spring, and then minus mg into 2x, gravitational potential energy. So this is like half m v squared plus 4v squared, that is 5v squared, right, plus half kx squared minus 2mgx. And as is routine, dE dx is 5 mv dV dx minus plus kx minus 2 mg equal to 0. So v dV dx is the acceleration of this mass. V dV dx is the acceleration of this mass. So v dV dx is minus k by 5m 2x plus 2g. The equilibrium position can be obtained by plugging in this equal to 0. So 10 mg by 5k, 10 mg by k is going to be the equilibrium position, right? Sorry? By 5. I'm sorry. By 5. I'm so sorry. 2g by 5. So x equal to 2g by k, 2 mg by k is going to be the equilibrium position, and the omega square for the oscillation is k by 5m. So the omega for the oscillation of this mass m is going to be root k by 5m. The time period is going to be 2 pi by omega. How many of you got this right? Okay, very good. Very similar situation. Now, while this mass m moves to the right by an amount x, this is the natural state of the spring. While this mass moves rightwards by an amount x, this pulley would move to the right by an amount x. It will then leave 2x units of string free. Those 2x units will appear along this, equally distributed on either side, x units this side and x units this side. That means it's going to result in the mass m descending by, the resultant descent of this mass by an amount x, yes or no. Which means the amount this has got displaced is the amount that this has got displaced. That means at a given instant they must have the same velocity v. They must have the same velocity v because they are getting equally displaced in equal intervals of time. So while this acquires a velocity v, this also acquires a velocity v, having got displaced x units downward. Energy expression then, the energy expression. Half mv squared into 2, right? This plus this. Plus half kx squared minus mgx. That's the energy expression. Yes or no? So dE dx 2mv dv dx plus kx minus mg must be 0. Again, v dv dx is minus k by 2m plus g by 2. The omega square for this oscillation is k by 2m. Omega is root k by 2m. Time period is 2 pi by. Yes or no? So now these are energy principles that are deployed to solve a variety of problems in simple harmonics now. To kind of complete the circuit, it's important that I introduce you to one more idea. I will still not say that the circuit would be complete by then. There would still be things that would be in abeyance. But one important idea, and don't lose heart, run out of steam. Listen to me carefully. A large number of you might already be knowing this, but then this would be a prelude to some more discussions on simple harmonic motion. One, let me define the following for you. If there is a point O, and a certain force F acts at a point P, there is a certain force of magnitude F acting at P. This is the line of action of the force, LOA. This is the line of action of the force, F. This is the point of application of the force. L is the perpendicular distance. L is the perpendicular distance of the line of action of the force from the point O. We define then what we call the moment of the force about O, moment of the force about O, or torque about O. O as tau O as F into L. L is the perpendicular distance of the line of action of the force from the point O, and this is the moment of the force about O. This L, the perpendicular distance of the line of action of the force from the point O, is also called the moment arm. It's also called the moment arm. The torque produced by a force about a point, this torque produced by a certain force about a point O, is a measure of the turning effect of this force about O, is a measure of the turning effect of the force about O. The force F acting on a rigid body will measure the acceleration of the center of mass. But let's say I have a rigid body and which is pivoted about O, and at a certain point of the rigid body a force F acts, then the extent or the turning effect produced on the rigid body with respect to O is going to be the torque about O, which is F into the moment arm. F into the moment arm. This torque or the turning effect about a certain point for a force is a vector quantity whose magnitude is this. Is a vector quantity whose magnitude is this. On most occasions, instead of talking of the direction of the torque is a vector whose magnitude is tau naught. It has a certain direction. But in most cases, we don't talk of the direction of torque. We talk of the sense of the torque. There is difference between sense and direction. A sense does not necessarily have direction, but direction always makes sense. All right. Coming back to physics though. So now, when we talk of the sense of this torque, like I said, that's a more practical requirement of a torque. That will give you a physical feel, insight into the whole idea. But when I talk of the sense of the torque about, what we do is, this is the moment arm, the perpendicular distance of flow from the line of action of the force. We mentally imagine or conceive a rod here. Mentally imagine that there is a rod here, which is pivoted at O. There is a rod here which is pivoted at O, right? And a force F acts like this, and a force F acts like this on the rod in this direction. Then this force F acting at this point of the rod, right, will cause the rod to rotate in the clockwise sense. Therefore, the turning effect of this force F about O is clockwise. The turning effect of this force about O is clockwise. And therefore, we say that the torque about O for this force F about this O is clockwise. The sense of this torque is clockwise. So, like I mentioned, clockwise is not a direction. But then, to convert a clockwise or anti-clockwise into a direction, this is what you need to do. Although that's not important, the important thing is the sense of the torque about O, which is not the direction, but then we can convert the sense into a direction. Literally. What you do is you take your right hand. Right. All of you have a thumb each. Curl your fingers of your right hand along the sense of rotation, right? This is how you curl your fingers, and watch your thumb. The thumb in this case goes into the plane of the board. That's the direction of the torque. We will not talk of the direction. In most cases, we will talk of the sense of the torque. Now, similarly, if a force F acts like this at a certain point P, and there is a certain point O here, then this is the line of action of the force. Then this L, the perpendicular distance, is the moment arm with respect to this O. This is the moment arm. The torque about O is F into this L. Now, what's the sense of this torque? Again, imagine a rod here. And a force F to be acting this way. Do you realize that this rod then would rotate anti-clockwise about O? And then we say that the sense of the torque about O, is anti-clockwise, right? Now, there are times when in a given situation, you're going to encounter simultaneously clockwise and anti-clockwise torque. In the sense, say this is a rigid body. This is a point O. There is a force of magnitude F1 acting this way. There is a force of magnitude F2 acting this way. There is a force of magnitude F3 acting this way. Right? Now, F1, for example, produces a torque about O, which is F1 into this L1. L1 is its moment arm about O. So it produces, realize that about O, this F1 produces a clockwise torque. About O, right? Because imagine a rod here to be pivoted at O, then this F1 would cause this rod to rotate clockwise. Here. Now, this is the line of action of F2. So this is L2. So F2 into L2 would be the torque about O because of F2. And again, imagine a rod here, a force F to be acting this way, then the torque produced is again clockwise about O, right? This is a force F3. The moment arm is L3. The moment arm is L3. And the torque that F3 produces about O, realize again, imagine a rod, a force F to be acting. And the torque that this force produces about O is anti-clockwise. Now, in a situation where you have simultaneous presence of clockwise and anti-clockwise torques about a certain fixed point, right? The net torque would be the algebraic sum of the clockwise and anti-clockwise torque. You can choose to call, for example, all the clockwise torques positive, all the anti-clockwise torques negative. So the net clockwise torque about O, the magnitude of the net clockwise torque about O would be F1 into L1 plus F2 into L2 minus F3 into L3. If this number turns out to be positive, then the net torque about O is clockwise. If this number turns out to be negative, then the net torque about O is anti-clockwise, right? Now, look, when we talk of equilibrium of rigid bodies, that are being acted upon by a bunch of forces, say F1, F2, F3. These are forces of magnitudes F1, F2, F3 acting in shown directions, right? Now, one aspect of equilibrium is what we refer to as translational equilibrium. Translational equilibrium would occur when the vector sum of all the forces is 0. Vector sum of, that means this force vectorially added to this force vectorially must be 0. That will produce translational equilibrium. That is, vector sum of all forces is 0. Is 0. And then we talk of what's called rotational equilibrium. Rotational equilibrium is the sum of, maybe the algebraic sum, if I talk in terms of clockwise and anti-clockwise torque, the net torque acting equal to 0 about any point on the rigid body, 0 will give me rotational equilibrium. Tau net about any point equal to 0 will produce rotational equilibrium. Now, one important fact that you might want to jot down: if a body is found to be in translational equilibrium, and if the torque about one point, the net torque about one point is zero, then the torque about any other point will be, then the net torque about any other point will also be 0. And the net torque about any other point will still be 0. Which implies, write down, which implies that if a body is in total equilibrium, total equilibrium means translational equilibrium as well as rotational equilibrium. Translational equilibrium as well as rotational equilibrium. If a body is in total equilibrium, then we can enjoy taking torque about any point of the rigid body. We can take torque about any point of the rigid body. We can take torques about any point of the rigid body and equate it to 0. Also write down taking torques about different points. Will produce different levels of algebraic convenience. See, when you have the option of equating torque to 0 about any point, then when you have freedom, that's when you'll have to be judicious. So you have the freedom in rotational equilibrium, you have the freedom of taking torques about any point and equating it to 0. And therefore, the onus lies on you to identify a very suitable point such that if you take torques about that point, it's going to give you an algebraic expression which would be easier to handle. Although taking torques about any point will give you the same final result, one would shorten the length of your journey, the other one would only make it a little more elaborate, right? Now, say there is a rod of mass m, uniform rod of mass m. So its weight acting through the midpoint, and say there is a force F1 acting at a distance a from the center of mass, F2 acting at a distance 2a from the center of mass, and the rod is in equilibrium, translational as well as rotational. So translational equilibrium would mean F1 plus F2 is mg. Rotational equilibrium means the net torque about any point equal to 0. Now, one of the things is, if there is a force F acting this way, and this is the line of action of the force, and you take any point P on the line of action of the force, then the torque about this point will be 0, because the perpendicular distance of P from the line of action is 0. So along the line of action of any force, the torque that this force produces about that point is going to be 0 all the time. I want to be able to solve for F1 and F2, given that the rod is in translational and rotational equilibrium, complete equilibrium. So for rotational equilibrium, let's say I take torque about the center of mass of the rod. Now F1 produces a clockwise torque about the center of mass. Do you realize that? This is F1, this is the moment arm, and the torque that it produces about the center of mass is clockwise? Yes or no? So about the center of mass, F1 into A is the torque that this produces. F2 produces an anti-clockwise torque about the center of mass. So minus F2 into 2A. This is the net torque about the center of mass. mg produces 0 torque about the center of mass. So this is 0. So using these two equations, you can solve for F1 and F2. You can solve for F1 and F2. What you could also do is, you could say take torque about this point. You could take torque about, let's say, point P. Now, what's the torque that F1 produces about P? F1 into 3A clockwise. F1 into 3A clockwise. What's the torque that mg produces about P? Mg into 2A and anti-clockwise and anti-clockwise. So minus mg into 2A. What's the torque that F2 produces about P? 0. So the net torque about P also is 0. So in this case, F1 can be readily found. So this is algebraic ease. This is algebraic ease. So that's when that's what I meant when I said it's important to realize what would be the best point about which you should take torque, so that you have algebraic ease at your disposal, right? So F1 is 2 mga by 3a, right? So 2 mg by 3, and once you know F1, F2 is mg minus 2 mg by 3, so mg by 3. Got me? Now, reason I had to give this to you is the following. See, this is a light rod pivoted here at O. Light rod pivoted at O. And there is a mass m at one end of the rod. There is a mass m at one end of the rod. But there is a spring a force constant K at some other point. Say this is A. This is B. Hey, it would have been, and I want to identify the nature of motion, simple harmonic, but the omega of oscillation of the mass m, given that the spring is connected somewhere else. Ideally, I would have liked something like this. This was the mass m. I would have liked a spring here. But when you displace the spring by a small amount, the restoring force will be proportional to the displacement. It's going to execute simple harmonic motion equal to root k by omega equal to root k by m, etc. If this was the position of the mass and the spring vertically below the mass. You realize why that's the case? For small oscillations, that means for small deviations with respect to the horizontal of the rod, very small deviations. Now, if the spring is here, ideally I would like to move it. Ideally, I would like to move it right here. But then I can't use force constant K of the spring. I would have to redefine the K of the spring now. K of the spring that gets shifted would be different. Why? Why? Look, if I shift a spring, then I will have to redesign and remodel the force constant of the spring. And how do I remodel the force constant of the spring? The moment I realign it. Let's say imagine that with respect to the horizontal, this rod gets deviated by a small angle theta. The rod gets deviated by a small angle theta. Now, two possible positions of the spring. One, the spring could have been located, this is B units, and this whole thing is A unit. Two possible locations of the spring, right here, force constant K, or it could have been here and would have been force constant K prime, would have been here force constant K prime. So if I want to shift the spring, the force constant here would have been K prime, Now, in this case, if the spring was here, it would have got compressed by this amount. And when the spring is here, it would have got compressed by, yes or no? At a distance x from the pivot, if this angle theta is small, at a distance x from the pivot for a point P, this length is going to be x tan theta, yes or no? X tan theta. This length is going to be x tan theta. But when theta is small, tan theta is approximately equal to theta. Tan theta is approximately equal to theta when theta is small, right? So then this would have been theta, x theta, tan theta to be replaced by theta in the event theta is very small and is in radian. So then this length would be b theta. The compression in the spring here would be b theta. X is b here, b theta. This would be a theta. This would be a theta, the compression in the spring here. All of it when theta is very small. The important thing is, I mean, this is one position of the spring, this is another position of the spring. And the force constants K and K prime would be such that, well, whether the spring is here or here, if these two are equivalent springs, then the torque of this spring about O must be the same as the torque of this spring about O. That's when they would be looked upon as being equivalent. These two springs would be looked upon as being equivalent if the torque about, say, O of one spring is the same as the torque about O of the, got me? Now, this spring has got compressed by an amount, b theta. So what's the spring force acting upward? F1, the spring force here is K into b theta, K into the compression of the spring, K into b theta. What's the torque that this spring force produces about O? Into B. Right? That's the torque that this spring produces about O. And if this is an equivalent spring, that means if you shift this spring here and you have an equivalent force constant K prime, and the torque of this spring must be the same as the torque of this spring about O. That's when they are looked upon as being equivalent. You know what I'm saying, right? So this is K into B theta into B, torque about O. If this is an equivalent spring, that means if you shift the spring, you have to modify K. K now becomes K prime. So this is K prime. What's the compression in the spring? A theta into A. That's the torque about O because of the spring. So the revised K is K prime here. So the revised K is K prime equal to K into B squared by squared. This is a very important concept, Shifting of springs must be accompanied with modification of K, right? So now if you had a spring here and a mass here, and you shift the spring here, it will have force constant K prime, it will have force constant K prime. So now the revised system, this system is remodeled as a mass m at one end, which is a units away, the spring of force constant K prime right below the mass m. Now for vertical oscillations of the mass m, the omega would be root K prime by m. Omega is going to be root K prime by m, where given K, they will tell you K, but K prime would have to be obtained. How? K into B squared by square. Right? So this is the shifting. This is the shifting equation for a spring. Shifting equation for a spring. Right? This is what you got to do when you shift the spring. You shift the spring. So if you look at problem 14, you'll imagine a mass m to be here, say, or it's not here. So if I shift this spring here, if I shift this spring to the right, then the revised K is going to be K1 prime. It's going to be K1 prime, where K1 into A squared must be K1 prime into B squared. K1 into A squared must be K1 prime into B squared. And therefore the revised K is K1 prime, which is K1 into A squared by B squared. That's the revised system. And now once you have this, get rid of this, and then this K1 prime and K2 are in series. There is a vertical oscillation associated with this mass, and the equivalent K would be K1 prime in series with K2 prime. So the K equivalent for K1 prime in series with K2 is going to be K1 prime into K2 by K1 prime plus. So the omega of oscillation is going to be root m by K equivalent, root, right, K by m, root K equivalent by m, root K equivalent by m. That's going to be the omega. Okay, attempt 13 and 15, please. Attempt 13 and 15. I'll join you in a little while. Now, one thing, of course, not all of you would be knowing this aspect of mirrors. But let me tell you, once we do geometrical optics, you'll realize that if I have a plane mirror, and if this is an incident ray, this is the reflected ray, and if the mirror is rotated by an angle theta, if the mirror is rotated by an angle theta, for the same incident ray, the reflected ray would rotate by, the final reflected ray would rotate by an angle 2 theta. The implication of this result is, if there is a mirror which is rotated out of its plane, I mean, if this is the mirror and it's rotated like this, then it will make no difference. But if this is the incident ray and if the mirror is rotated like this out of its plane, then the reflected ray would rotate by 2 theta. Now the implication of this is, see, if this is a mirror, and an object moves like this, then its image would move like this. If the object moves vertically, the image would also move vertically. If, however, the mirror is rotated by an angle 45 degrees, if the mirror is rotated by an angle 45 degrees, then despite the fact that the object moves vertically, the image will move horizontally, because the image would have got rotated, the motion of image would have got rotated by 90 degrees. So if the mirror is rotated by 45 degrees and the object moves vertically, then the image would move horizontally, right? Now the next problem is precisely based on this idea. This is the vertical position and this is the actual position of the mirror. This insect on this mass m is moving like this, and therefore its image, realize, is going to move like this. Its image would move like this. This is the object moving vertically, the image is moving horizontally, right? Now, the maximum velocity, maximum speed of the insect, is going to be a omega, where omega, of course, you can see is root k by m. At the mean position, it's going to execute simple harmonic motion and would have a V max a omega downwards, and the V max of this, the absolute V max of the image, would be, the image will execute simple harmonic motion about a mean position, say here, and at its mean position, this would have V equal to a omega. While this guy executes simple harmonic motion with omega, amplitude a, this guy executes simple harmonic motion horizontally with amplitude a and angular frequency omega. And therefore, at this juncture, the relative speed would be the maximum, right? Velocity of the insect relative to the image. Velocity of the insect is a omega like this, right? Velocity of the image is a omega like this. Velocity of the image is a omega like this. So velocity of the object with respect to the insect is going to be velocity of the object minus the velocity of the insect. So the relative velocity is going to be a omega for the object, and a omega like this, that is negative of this velocity is a omega like this, and the resultant of these two will give me the relative velocity, velocity of the object, and this is negative of the velocity of the image, right? So this is going to be a omega root 2, a omega root 2, where omega is root k by. Got me? So what I'm going to do is I'm going to shift k1 here, and I'm also going to shift k2 here. So let's say when I shift k2 here, I put it upside down. K2 becomes like a k2 prime here, and k1 becomes like a k1 prime here. This is what I'm doing. And then k1 prime and k2 prime would be in series on this mass m, and k effective is going to be k1 prime into k2 prime by k1 plus, and omega would be k effective by m, square root of that. So now what you do is, for a moment, imagine C to be pivoted. Imagine C to be pivoted, right? And cause the spring to go down here. Cause the spring to go down here, right? When you cause K1 to go down here, bringing it to K1 prime, then very clearly K1 into 9a squared, taking talk about C, K1 into 9a squared must be equal to K1 prime into 4a squared. So the K1 prime turns out to be K1 into 9 by 4 is K1 prime. Similarly, imagine B to be pivoted for a moment, right? And bring K2 to this position, causing it to be, say, I can always make it upside down, K2 prime, alright? And then if I imagine B to be pivoted, then K2 prime into A squared will be equal to K2 into 9A squared. So K2 prime is going to be 9 times K2. So I know K2 prime, I know K1 prime, and then I know the K effective for the system, K1 prime, K2 prime by K1 prime plus K2 prime, and then the omega of the system is root K effective by, is the omega of the system. Now in my last sheet, can I write this up? Now that I have at least told you what torque is all about, you know, I can address some more issues. There was this platform. This was moving like this. This was another roller moving like this. mg the separation between horizontal separation between the rollers was L. Now, and the coefficient of friction between the roller and the platform was mu. Coefficient of friction was mu between the platform and the roller. Now, since they were equispaced, it was symmetric. The normal reaction here was N. The normal reaction was N here originally, right? Because they are equispaced from mg. This will produce a clockwise torque N into L by 2. Anti-clockwise torque. This will produce a clockwise torque N into L by 2. The torques about the center of mass would be 0. It will not topple, right? And N plus N would add up to mg. So N would be mg by 2. Now, if you look at this point on the roller, this point has a velocity to the right. This point has a velocity rightwards. So the frictional force on the roller at this point would be leftwards and would be mu n. Would be mu n on the roller. So on the platform, it's going to be mu n to the right. Because if the frictional force on the roller is leftwards, the roller will exert on the platform a rightward frictional force, yes or no? On this roller, the velocity of the topmost point is leftwards. So frictional force mu times n would act to the right. So the roller would exert on the platform a mu times n to the left. Everything will cancel off, right? Now, when I shift the platform by an amount x to the right, retaining the positions of the roller, if I slide very slowly the platform by an amount x to the right, what happens? I've shifted the platform by an amount x to the right. So then this end would be, this was originally at a distance L by 2. So now it will be L by 2 minus x. This was originally L by 2. So now, I'm sorry, this would be L by 2 plus x, it's moved further away. So L by 2 plus x, this has moved away. And this has moved closer, to this. So this would be L by 2 minus x. Minus x. And the revised normal reactions are N1 and N2. Where for translational equilibrium, N1 plus N2 must add up to mg. mg. The frictional force acting on the roller now, on the platform now, instead of being mu n, it's going to be mu times n1 to the right, and from this end, it's going to be mu times n2 to the left. Right? So when I have moved it by an amount x to the right, there is a net force mu n2 minus mu n1 acting to the left, which could be looked upon as a restoring force, right? When I have displaced it by an amount x to the right, this was an equilibrium position. Net of all forces acting on the platform horizontally was 0. But now net of all forces is not 0 because n1 is no longer equal to n2. So the net force or the restoring force is going to be mu times n2 minus n1 to the left. Yes or no? Right? But then it's not toppling. Even in this revised state, it's not tilting. So the torque about the center of mass will still be 0, net of all torques. So when I take torque of N1 about the center of mass, N1 into L by 2 plus X, that must be equal to the anti-clockwise torque N2 into L by 2 minus X. Yes or no? So this gives me N2 minus N1 into L by 2 is X into N1 plus N2. Right? Hey, but N1 plus N2 will still balance the weight. So this is mg into X. Right? Where X is the displacement from the equilibrium position. Right? So that gives me like a N2 minus N1 equals 2 mg by L into X. And the restoring force then is mu times 2 mg by L into X. So the restoring force is proportional to X. So the motion is simple harmonic, and the force constant must be this. This must be the force constant of the motion. So the omega of the motion is root k by m. So 2 mu g by L must be the omega of the oscillation, and the time period would be 2 pi by omega. Got me? You know, when they schedule hours to a topic, it's such an irrational thought. I mean, there is actually no end to anything. So men may come and men may go. SHM goes on forever. All right. So far, we've sidetracked the mass of a spring, and said, all right, we ignore the mass of a spring. Spring is massless. Dealt with situations. About time to quickly look, and it's an easy thing because you have all the tools at your disposal to uh, to, to write down the equations in which mass of a spring is factored. So we now have a system, typical system, with a spring of length, natural length L and mass m, and therefore mass per unit length m by L of the spring. A spring, let's say, that has mass ms. A spring that has mass ms, mass per unit length is lambda of the spring, a uniform spring. And there is a mass connected to one end of the spring. This is the natural state of the spring. I produce oscillations on the mass, and at some instant, when the mass has got displaced by an amount x, I look at this and it has a velocity v. At this juncture, I will write down the energy equation. An intermediate equation. E, kinetic energy of the mass, elastic potential energy of the spring. Now the spring has mass, so it has kinetic energy. So there is kinetic energy of the spring too. Yes or no? So there is kinetic energy of the spring. The only task ahead of us is to be able to find the kinetic energy of the spring, right? This end of the spring is rigidly attached to the wall and its velocity will be 0. This end is integral with the mass m and it will have a velocity v to the right. We will assume for convenience that the velocity increases linearly, uniformly from 0 to v over a length L of the spring at this, right? So let me find out the kinetic energy of the spring in this state. In this state, so the intermediate state of the spring is, this is the spring, mass of the spring ms, let's say L is the length of the spring at this juncture, and this end has velocity 0, and this end integral with the mass has velocity v equal to v, same as that of the mass, right? So the velocity increases from 0 to v over a length L, look at a point at a distance r. Look at a point at a distance r and think of a small segment dr, length of the spring dr. Now, what would be the velocity of the point at a distance r? Well, the increase in velocity over a length L, the increase in velocity is v for a length L. So, for a length r, the increase in velocity is r. V by L is the change in velocity per unit length. So, for a change in length r, this would be the change in velocity from 0 to this. So, the velocity at this point of this mass element here is going to be V by L into r, yes or no? That's the velocity of this element here, right? What's the mass of this element? The mass of this element is ms by L, mass per unit length, into length dr. That's a mass. This into dr is the mass. This is mass per unit length into the length of this segment is the mass of this segment. Now, half of this into this is the mass into square of the velocity. That's the kinetic energy of this segment. That's the kinetic energy of the segment. ms by L into dr is the mass. Half of the mass into square of the velocity of this element will be the kinetic energy of this element. dk. That's the kinetic energy of this element. The total kinetic energy would be the sum of the kinetic energies of the various drs where r runs from 0 to L. Yes or no? So, the total kinetic energy, ms by L, etc. is constant, would be sum of all of this where r runs from 0 to L. Which is half of ms by L into v squared by L squared into L cube by 3. Which is half of ms by 3 into v squared. Half of ms by 3 into v squared, yes or no? Right? Now, come back to this. This is half mv squared, half kx squared plus half of ms by 3 into v squared. That's the kinetic energy of the entire system. That's the total energy of the entire system, which is half of m plus ms by 3 into v squared plus half kx squared. The only difference between the earlier equation and this equation is, in the earlier equation you only had m. Now instead of m you have m plus ms by 3. For the earlier equation, what was the omega? Omega was root k divided by small m when the mass of the spring was negligible. Now instead of small m you have small m plus ms by 3. So the revised omega is going to be root k. The k remains the same though, right? Root k divided by, now the effective mass is m plus ms by 3. So in situations where the mass of the spring is not negligible, the spring mass is incorporated by adding to the original mass 1/3 the mass of the spring. 1/3 the mass of the spring would have to be added to get the omega of the system. Got me right on this? One last bit. I think it just slipped out of my mind to communicate this earlier, but you know, just to make the digression kind of complete. Uh, suppose on a given particle, you superimpose two oscillations, right? One, there is x forced as per x1 is a1 sine omega t, and there is another x forced on the particle x2, which is a2 sine omega t plus say theta. These two oscillations are superimposed on a particle. Now the net x on the particle would be the algebraic sum of these two. So the net x on the particle is going to be actually x1 plus x2, which is going to be a1 sine omega t plus a2 sine omega t plus theta. This would be the x on the particle because of this superimposition of two oscillations, which I could write as a1 sine omega t plus a2. I could expand this sine a cos b plus sine b cos a, a2 sine omega t cos theta plus sine theta cos omega t, right? Which could be written as a1 plus a2 cos theta into sine omega t plus a2 sine theta into cos omega t. Hey, which is like some capital A sin x plus capital B cos x, right? Capital A sin x plus capital B cos x could be written as root a square plus b square, a by root a square plus b squared way back in trigonometry, sin x plus b by root a square plus b square cos x, where you can call this as sin cos phi, and then this will turn out to be sin phi, leaving you with root a squared plus b squared sin x plus phi, where what is tan phi? Tan phi is b by a. Tan phi is b by a. Right, recall this. Now using the same thing, this is like a sin x plus b cos x. It could be clubbed together as root a square plus b squared. And what's root a square plus b squared in this case? That is this square plus this square is a square, a1 squared plus a2 squared plus 2a1 a2 cos theta. Yes or no? That's a squared plus b squared. That's a squared plus, this is a, this is b. So this is what happens. So we have like root a1 squared plus a2 squared plus 2a1 a2 cos theta sin omega t plus phi, where what is tan phi? Tan phi would be b by a. Right? Now, the way to interpret this is as follows. Eventually, the resulting motion would have this as its amplitude and this as its phase. The amplitude of the resulting motion of these two, these two differ in phase by theta, the resulting amplitude of the motion emerging out of this is going to be root a1 squared plus a2 squared plus 2a1 a2 cos theta. That's the amplitude of the resulting motion, and the phase of the resulting motion tan phi would be a2 sin theta by a1 plus a2 cos theta, where theta is the phase difference between these two oscillations, right? Now, instead of doing all this trigonometry, what you could have done is, there is a geometrical way of handling all this. There is a geometrical way of handling all this. This I can think of as a zero phase entity and of a maximum value a1. This is an entity of phase theta and of maximum value a2. Think of a vector. Think of this as a zero phase line. Along the zero phase line, draw a vector of magnitude a1. And now, if this is zero phase, a line inclined at an angle theta could be looked upon as phase theta. Along the theta line, draw a vector of magnitude a2. Now, with a1, a2 being looked upon as vectors, realize that the diagonal of this parallelogram is the resultant of these two vectors. If I mentally imagined a1, a2 to be vectors, then the diagonal of this parallelogram would be the resultant of these two vectors. And do you realize that the diagonal of this parallelogram is root a1 squared plus a2 squared plus 2a1 a2 cos theta, right? That means the resultant of these two would be the amplitude of the resulting motion, right? And what would be the phase of the resulting motion? Do you realize that this phi, actually from parallelogram law, this phi is actually a2 sin theta by a1 plus a2 cos theta. So the angle that this resultant makes with the zero phase line would be the phase of the resulting motion. So this resulting motion, if I superimpose x1 and x2, I get a sin omega t plus phi, where a is this and phi is this angle, right? And representing a1, a2 in this sense is called a phasor diagram. And the utility of this is best obtained when you have number of displacements of this kind to be superimposed. You could, for example, have x1 equal to 2 sin omega t, x2 equal to 3 sin omega t plus pi by 3, x3 equal to 4 sin omega t minus pi by 3. So now x1 plus x2 plus x3 should turn out to be some a sin omega t plus phi. Our job is to find a and phi. All that we do is we do a phasor representation of x1, x2, x. The phasor for x1, this is the zero phase line. So along the zero phase, draw a vector of 2 units magnitude. This is zero phase. Now x2, phase pi by 3 with respect to the zero phase line, plus pi by 3. 3 units and plus pi by 3. Right? And then 4 units and minus pi by 3. If this is zero phase, then this is pi by 3 less than zero phase. Right? So then this is 4 units and then this angle is pi by 3 with a negative sign. Right? The resultant of this vector and this vector would have a magnitude equal to a, And the angle that the resultant of these vectors makes with the zero phase line will be the phase phi of the resulting motion, right? So all that one needs to do is, in this case, you don't need to use parallelogram law. You could look upon this as the y direction, look upon this as the x direction. So the x component of the resultant is going to be what? 3 cos pi by 3 plus 2 plus 4 cos pi by 3. That's the x component of the resultant. The y component of the resultant is 3 sin pi by 3 minus 4 sin pi by 3. So this is ax and ay. What's the resultant a? The resultant a is going to be root ax squared plus ay squared. So we then have ax along the zero phase line, ay in the perpendicular direction, and then a would be this root ax squared plus ay squared obtained, and this angle would be phi. Do you realize that this angle would be phi? Where tan phi would be ay by ax. Perfect. Tan phi would be ay by ax. So phi would be known, a is known. So the phasor diagram, I mean, in my first sheet, you would have seen a couple of problems based on this phasor representation. So this is what you do. All right. Huh? No, because I have not taught gravitation.